I'm a drummer, man.
Everybody thinks they're a drummer. Now he's dropping his drumsticks.
My six bell.
It's not even a drum, it's a plastic bucket.
No, it's a drum.
It's a plastic bucket.
You need the glasses.
All right.
Okay, podcast 3.2.
All right, 3.2.
By the way, 3.2 is a bit of a typo, or actually 3.2 is correct. Our last one should have been 3.1. We apologize.
I think we called it 2.2. So Mr. Bergman still not quitting his day job.
Okay, I will keep my day
Back
job.
to chemistry we go.
I am now a drummer with my sticks.
He's a drummer, kazoo player, ukulele guy.
Yeah. So, today we want to learn about how to do some problems. We're still kind of doing review stuff, folks. This is not new.
Yeah, nothing
we
new.
do have a new thing, though, to teach you. So,
yes.
But not until a little bit later. Okay.
So we're going to kind of go pretty quickly through the old stuff.
Percent to mass, mass to moles.
Divide by small,
And
times still whole.
I'm still whole.
You guys all remember that. There's a poster in both of our rooms.
So we're going to do this problem, this example, quite quickly.
Yes,
so
here we go. We've got a bunch of percentages of elements in a compound. We're going to just arbitrarily change those percentages into masses. We're just going to call them grams.
So 10's molar mass is
118.7.
So 118.7 grams.
Cottrell, could you please come
One
down?
mole. They're asking for that old Mr. Cottrell. He must be in trouble. Okay.
All right.
And what have I got?
What do you got? Iron, 12.4.
12.4 grams over 1.
Is that a 12?
That is a 12. You can't read very well, can you? And that's 55.8 grams in 1 mole. And then I've got
16 carbon.
16 grams of carbon. I'm not putting the carbon on here since I'm putting it out here in the iron. Oop, that looks like chlorine. Still looks like chlorine. That's carbon. There's 12 grams in 1 mole. And
18.8.
I have 18.8 grams of nitrogen. Now I wrote the nitrogen. Okay, well, no big deal. 14 grams in 1 mole. And now I get my calculator out. So in the 10, 52.8 divided by 118.7
is 0.445.
44.5. And then 12.4 divided by 55.8
is
point dos. All right, I'm trying to do my Spanish.
Nah.
Not very good.
1.33333333333.
And this last one is
1.34.
Now divide by percent to mass. We did that.
Yep.
Mass to mole.
Yep.
These are all moles, by the way. I didn't label like I should have probably. Divide by small. The smallest number is the 0.22222. I can do this when this is 1. If I take 0.22222, this I can see is 2, and this I don't know.
That
I think it's
one
6,
is, whoops, I did it wrong. 1.333 divided by 0.2222. There we go. Is 6. You're right. And then 1.34 divided by 0.2222 is 6.
So you've got how many? We've got 2 10s. So S in 2.
Yep.
F E
One of those.
I'll put a 1. You don't have to really do that. And then C 6
H 6.
N 6.
Oh, N 6. Yes, sorry.
Yeah, so. Yeah, this actually is a different formula when you write it out with a polyatomic ion, but we won't worry about that. That's how you would do that. No big deal.
There it is. Empirical formula.
Okay.
Percent to mass, mass to mole, divided by small,
Times
still whole.
still whole.
Next one is empirical formula's cousin.
Molecular
which is
formula.
Molecular formula.
Now, if you're going to do a molecular formula,
Okay.
so a molecular formulas are just
I know, looking at our blanks, what did we mean here? Those are the actual formulas.
the actual formulas, that's right.
Not just the simplest.
Not the simplest. Oh, actual formula. I knew
Yes.
this. I wrote it. And I can't remember. It's or not just the simplest ratio.
Yeah. So, an empirical formula is the lowest whole number ratio of the elements in a compound. The molecular formula is the actual formula of all the elements.
You know, I have an analogy, Mr. Sams, that helps us to remember this.
Good times.
Here is Mr. Bergman right here. And as you know, Mr. Bergman has, what? How many fingers and how many hands? What is the ratio of fingers to hands?
I think most people, that's 5 fingers per hand.
No? All right. The ratio is 5 fingers to 1 hand. But now, Mr. Sams, look at me right now with your eyeball.
1, 2.
How many fingers
10,
do I actually? I have
fingers.
10 fingers and
2 hands.
So this is the ratio, correct? If I can write the word ratio, the ratio here, that is the simplest.
That's the lowest whole number ratio.
But in actuality, I actually have 2 hands and 10 fingers.
Yes, you do.
So this is like the empirical formula, and this is like the molecular formula. There you go. It
I
actually,
like it.
a student taught that to me years ago. I didn't learn it even myself. One of my amazing students, who's probably like a doctor making triple his teacher's wage these days. Okay.
You mean doctors make more than teachers do?
Well, you know, not in reality, in money, but you see, we get much better strokes from our amazing students.
That's true.
And so we have job satisfaction.
They
only heal people. What's up with that?
Yeah, job satisfaction. You got to remind me that periodically.
Yeah. It would be nice to make a couple more dollars. Nevertheless, okay, molar mass is, and you just basically, how would you know to go from that I had 10 to 2? You'd say, well, you'd actually could weigh it. Well, let's just do an example. You guys know how to do this. So let's just do an example. So let's determine the molecular formula. Basically what we're going to do is we know the molar mass, you see, of this particular compound is 306. So let's just do the percent of mass to mole, divide by small, times to whole.
All right, so just
sodium is,
as a note here, wow, I love all the announcements going on today.
Soccer is going on now, ladies and gentlemen.
Yes, it is.
And those in internet land, guess what? They have soccer now.
Yes, they do.
And then phosphorus is...
phosphorus, 30.4%. We're still 30.4 grams. So, by the way, when you're doing molecular formula problems, always start by finding the empirical formula first. That's what I was trying to say before I was interrupted by... Hey, look, we're going to get interrupted again.
It's picture day, ladies and gentlemen. In oxygen, this is 16 grams in 1 mole. Hopefully you can hear me over the announcements. I'll talk into the microphone.
Perhaps you should play your drums some more.
Oh, ding-a-bing-bong. All right, let's just get this. We have a calculator out.
Percent to mass to mole. So we've got 22.5 divided by 23, and we got 0.978. 30.4 divided by 31 is 0.981. And then 47.1 divided by 16 is 2.94.
I see the smallest number is about 0.97.
Yeah, it's looking like that to me, yeah.
So I can do the first 2. That's close enough to 1 for all intents and purposes. I'm going to call that 3. Am I correct?
Yeah, I would say that's 3. It's 3.0 something.
So it's NaPO3. Now, if it's NaPO3, that is called the what formula?
That is the empirical formula. That is the
so
lowest.
We know that the molar mass of this is 306 grams per mole.
Yes.
Now, that's the molecular or molar mass,
right.
But we can find the empirical mass.
Let's do that.
So if I find 23 for sodium, phosphorus is 31, oxygen is 16. If we add that all up,
102.
I get 102 grams per mole. Think of this as my hands. You see, I have 102 grams of hands.
Yes.
Actually, in my
one
ratio,
hand.
In one hand, this is like one hand. And my total weight of hands is 306.
So in this
How many
case,
hands do I have?
It looks like 3 hands.
Because if you take 102 times what, you get 306. Of course, that's 3. So what this formula is incorrect, or it is the empirical formula. The molecular or actual formula would be Na3P3O9. You just triple them all because this number is a 3. You guys remember that. Actually, that would be Na, I can't write, Na3PO3, 3, sodium phosphite, if you recall. They just write it differently, of course.
Why is there a 3 outside the parentheses? I don't think that exists. I think we just made up something.
You are correct.
Because phosphite has a -3 charge. I think we just made up a compound.
I think Mr. Beckman made this problem up and was going too fast. But there's no such thing as Na3PO33.
But that doesn't mean you can't do the problem.
Well, so what? Okay.
Yep, moving on.
It's moving on, and it's going slow. We're waiting for the next screen to appear. Here we go.
There we go.
Now,
okay.
This is a particular issue, ladies and gentlemen. We have a more complex problem. And we need to kind of work our way through some of these more complex problems. And just kind of bear with me as I help to solve this. This is an interesting problem. I'm talking about the chemical propane. Many of you probably heat your house with propane gas. You got a big white tank that heats your house. Those in internet land, we live in kind of a rural area. A lot of people heat their houses with propane.
And it gets really cold.
It gets cold where we live. Yes, and so here's our problem. Now notice here we have gram numbers instead of percentages, but the rule still applies. Percent to mass to mole, divide by small, times to whole. But that's not actually the read. Let's read this problem carefully. All right, basically, complete combustion of propane produced this many grams of carbon dioxide and this many grams of water. So to start this out, we need to write a balanced equation. Now, one thing we know about the propane, I think it said it somewhere, is it a compound that contains only carbon and hydrogen. So I'm going to call it a Cha compound. Now, I do not know what the value of, if it's, is it C1H4 or whatever, we need CXHY. We don't know what that is, and it's a combustion problem, so react it with oxygen. So this is a chemical reaction, like a balanced chemical equation, but we really can't balance it, as you'll see. It produces carbon dioxide and water.
Always. Anytime you combust the hydrocarbon.
And you might be tempted to try and balance these equations, but you cannot, because we do not know what these numbers are. That's the question. What are those numbers?
Yes.
Now, we do know a couple of pieces of information. We know that we have produced
2.641 grams of carbon dioxide, and of water we make 1.442 grams.
So the question is if we know how many grams of products there are, can we determine this formula? And the answer is yes, we can. The key is to find out the mass of the individual elements, the carbon and the hydrogen, and in some case the oxygen. This one doesn't have that particular problem. Now we're going to actually make use of the concept of the percent composition to do this. So I'm going to do the carbon first. Now here I want you to understand that the carbon on the left side is only in the CH compound. And on the product side, the carbon is only in the carbon dioxide. That's a CO2.
Yes. And by the way, the law of the conservation of matter says whatever the mass on one side of the equation is of the carbon will equal the mass of the carbon on the other side of the equation. That's important.
So if I know the mass of the carbon on the product side, that is equal to the mass of the carbon on the reactant side. And that's what I'm going to figure out. I'm going to say the amount of carbon will be 2.641 grams of carbon dioxide over 1. Now watch what I do. It's a gram-gram ratio. I'm going to say that there is grams of CO2 for grams of carbon. Now these are just from the molar masses from the periodic table. Now the molar mass or atomic mass of carbon is 12, and the molar mass of carbon dioxide is 44. 12 plus 16 plus 16. Now if you look carefully, what's going to happen is the grams of the CO2 is going to cancel out with grams of carbon, and I get 0.720 grams of carbon. You see, this same principle applies to, I want to find now the mass of the hydrogen. And so for the hydrogen, all of the mass of the hydrogen on the left side is equal to the mass of the hydrogen on the right side. And all the hydrogen is, in this case, in the CH compound, and all of the hydrogen is in the water on the product side. Got it? So I simply will take the 1.442 grams of water. That's what I know, not grams of hydrogen, but grams of water. And then I'm going to say grams of water from the periodic table. It is, of course, water weighs 18 grams in a mole. And this will be, now careful, 2 grams of hydrogen. I'm going to go simply H because there's H2O, and each hydrogen weighs 1, of course. And this is 0.160 grams. You see, ladies and gentlemen, I now have grams, and that percent to mass, and I have
what
mass.
What is that grams of, Mr. Bergman?
Grams of hydrogen. Thank you, I didn't write that down. This is the mass, percent to mass to mole, divide by small, times till whole. So if I now do that, and I do my carbon first, I have 0.720 grams, and I will then say there's 12 grams in 1 mole, and that comes out to?
That comes out to 0.06.
0.60 moles, and the hydrogen was 0.160 grams, and of course the molar mass of hydrogen is 1 gram in 1 mole. That's pretty easy, and that's 0.160. Divide by small. The small number is the 0.060. 0.0. You know, folks, I'm going fast, and I understand that I am. You're going to probably need to slow and pause this occasionally.
And back it up.
Yeah. Okay. So. Percent to mass to mole, divide by small.
Times till whole.
Now notice,
those are not whole numbers, Mr. Bergman.
So we need to multiply. What number could I multiply these by, particularly looking at this fraction here?
Well, 0.6666666 is 2/3. If you look at it as a fraction.
2/3?
2/3. So to get rid of things as a fraction, you multiply by the denominator. So let's multiply by 3.
So that's going to be 3. 1 times 3 is 3, and 2.67 times 3 is 8. So the formula is simply C3H8.
Don't believe us? Go watch a couple episodes of King of the Hill where Hank sells propane and propane accessories. Mr. Bergman doesn't know what that is.
I don't watch that show, so I have no idea what you're talking about. I don't watch much TV.
I don't have TV anymore either, but I used to watch it a lot.
Okay, now we're going to do a problem that's a little bit more complex because this chemical has oxygen. So galactose is a brain sugar, and it's found in dairy products, in sugar beets and da-da-da. Okay, basically, now we have the mass of the galactose. Now, I'm not sure it says this. I could tell. This is not a Cha compound, but a Cho compound.
That's right.
That's going to react with oxygen to make carbon dioxide and water. Now, how many grams? Tell me the numbers that we know, Mr.
We have 2.315 grams of galactose. Carbon dioxide is produced, 3.953 grams of that. And of water, we have 1.389 grams. Now, it also gives us that the molar mass of galactose is between 172 and 186, somewhere in there. And this asks us for the empirical and molecular formula of galactose. That's why the molar mass is given, because we need to find the molecular
That's where we'll
formula.
double it with the hand analogy.
And we'll take care of that later. Right now, let's just
yeah.
focus on the combustion problem and the empirical formula.
So now I'm going to do each of my elements. I have carbon, and I have hydrogen, and I have oxygen. I'm going to do this a little bit differently than I did the last one, not to just totally confuse it. I'm going to add one additional step, which sometimes is useful on a couple of problems I know you're going to be asked to do on your homework or your classwork. For the carbon, I'm going to work from the carbon dioxide. So I'm going to say 3.953 grams of carbon over 1. Then I say 12 grams of carbon over 1 mole. Now I'm going to add one more step, ladies and gentlemen, because since I know the mass of this compound, I'm going to convert this to a percentage. And then I'm going to say, well, actually, let's just do this. And so I get, what is 3.953 divided by 12, Mr. Sams?
That's 0.329.
But I want to convert that to a percentage. The total.
Would that be moles, Mr. Berman?
That would be moles, thank you.
Did you do something wrong, Mr. Berman?
I didn't do this right. Because I want grams.
Yeah.
Let me do the carbon again. That would be 3.953 grams of carbon dioxide. Sorry about that, ladies and gentlemen. And then I'm going to do the 44 grams of CO2 to 12 grams of CO2. And I get...
That gives us 1.08 grams of C.
Of carbon. Now, what I'm going to do, ladies and gentlemen...
Can you change your numerator there next to 12 there? 12 over 44? You have CO2 written. That should be C.
Oh, carbons, yes, indeed.
There we go.
And I'm going to divide by 2.314 grams and times it by 100 to get a percentage. And so what is my percentage of carbon?
That is divided by 2.314 times 100. That is 46.6% carbon.
So 46.6% carbon. That's what I do that. I want to go to percentages, and you'll see why for more complex problems you need to. For hydrogen, I'm going to take the grams of water, which is 1.389 grams of water, right? Yep. And I'm going to do the 18 grams of water on the bottom and the 2 grams of hydrogen on the top. And the terms of the total grams is 0.1. You may need to just get your calculator out. 54 grams, and then divide by the total mass of my compound, which is 2.315
times 100.
Times 100 to get a percentage.
6.67%.
6.67%. Now, guess, ladies and gentlemen, how am I going to get the oxygen? The problem with the oxygen, if you were to try and use the method I just did, oxygen is produced in 2 different compounds, both the water and the carbon dioxide. So, and also in the reactants, we have oxygen in galactose and also in the oxygen. So it is impossible to get it in that method.
Mr. Bergman?
Yeah.
Don't most percentages usually add up to 100?
That's exactly correct. They add up to 100%. So I have my total percent, of course, is 100. That would be equal to the carbon, and the carbon percentage was 46.6 plus the 6.67 plus X, if you will. This is the oxygen, and that, if you subtract it out, the oxygen is 46.7%. Now I have percentages. Percent to mass, mass to mole, divide by small times to whole. So let's go through this here. I'm going to do my carbon, my hydrogen, and my oxygen. Now from my percentages, the oxygen was 46.7%. The hydrogen was 6.67%, and the carbon was 46.6%. Now I'm going to convert. These are like grams, so I'm just going to put a G next to each of these. So I'm going to say 12 grams, 1 mole, and that comes out to 2.9.
Nope, 3.88.
3.88 moles, and this is going to be 1 over 1 gram and 1 mole. I can do that. That is 6.67 moles. I don't even need a calculator. This is 16 grams in 1 mole.
2.92.
2.92. Smallest number is the 2.92. So the oxygen gets a 0. It gets a 1. I can't think here. Divided by 2.92. I'm going up. I don't know why, but that's where it is. Is that 2, Mr. Sams, or is that got a fraction? Whatever.
Which one there? I'm sorry.
Give me one of them.
Okay, 3.88 divided by 2.92. Sorry, I was looking at my calculator and it was doing weird things. 1.33 on that first one there. And then 6.67 divided by 2.92 is 2.28. And then that bottom one is 1. So
this is probably a bit of a weird problem.
Looks about like 3.
We're going to call that a 3. So 1.33 times 3 is
4.
4. 2.33 times 3 is 7. And this will, of course, be 3. So this will be C4H7O3. This is called the what formula?
That's the empirical formula. That's our lowest.
That's the empirical formula. So if the empirical formula is C4H7O3, and the molecular mass is equal to 172 to 186, we then need to figure out, what does this add up to, Mr. Sams?
That's what I'm working on right now.
The empirical weight of this is equal to
12 plus 4 plus 48 plus 7, 103.
103 grams per mole. So, of course, you need to be able to double or triple it or leave it the same. And I think that we probably must have the molecular mass wrong. It must be somewhere between 200 and 250. I think that must be a typo.
That's got to be it. Must be a typo.
That's the typo there.
Got to be.
And so what would you need to do to make it so it fits in that range?
I would say we double that.
We would need to times it by 2. So the formula for galactose is C8H14O6. And if you believe that...
And it may or may not be. We're not real sure.
We think there's an error in our problem. But okay, but the method is the same.